All right, so last time we introduced this chi-squared interval for sigma. Important thing to remember is, probably the most important thing to remember, is that we're no longer doing a confidence interval for mu. We're not estimating the average. We're estimating how much variability there is in a population, okay, based on a sample. So this is the form for our confidence interval. I know they look the same, but remember we're going to have two different chi-squared critical values. So the big one goes here, and the little one goes there. All right, so let's take a look at an example. So then the first example in the notes is this one. Move it over a little bit. All right, so it says the sample of size 27 is taken. Take the sample and find out the standard deviation is 3.9. So what is the 27? Sample size, that's n. And what is the 3.9? That's s, sample standard deviation. Okay, so the first thing I'm going to ask here is, what's the point estimate for sigma?
3.9.
S is probably going to be our best estimate for sigma. Now, one thing I should mention is, like, when we did a point estimate for mu, we just said, okay, it's x bar. X bar is a really good point estimate for mu. It's unbiased and has some other nice properties. The bad thing about S is actually a little biased, which means on average it's going to be off a little bit. So S may not be a perfect point estimate for sigma, but it's the best that we've got. So our point estimate for sigma is going to be S, which is 3.9. So what I wrote there, I know my handwriting is horrible, but it says it's not perfect, but it's the best we can do. So and when I ask for a point estimate for sigma, just give me S, even though we know it's maybe a little bit biased and maybe not the best one out there. Maybe we could do better, I don't know. All right, so number 2, we want to get a 95% confidence interval for sigma. We're not doing a confidence interval for mu, we're doing a confidence interval for sigma. Okay, so when we do this confidence interval, we're going to have a left and a right endpoint. The numerator is going to be the same for both of them, right? It's going to be n minus 1. So n is 27, so n minus 1 would be 26, right? Times, not s, s squared, yeah. So that's important to leave that out. So this will be 3.9 squared. And then we have to divide by the correct chi-squared critical values.
So the right's on the left, right?
Yeah, so let me grab the table here and take a look at this. First thing, sometimes people confuse the chi-squared and the t tables. Don't do that. And hopefully you won't, right? Because the t-table just has one column for each confidence level. The chi-squared has 2 different columns for each confidence level just because of the nature of the density curve. So we want a 95% confidence interval. So this is the chi. Notice it says, when we're doing the chi-squared, it says chi-squared on top. How many degrees of freedom should we be using here?
6.
Right. N is 27, so we're going to use 26 degrees of freedom. And we want 95, right? So we're going to go down. So if I were going to follow this, I'd say, okay, well, here's 26 degrees of freedom, and 95 is
3 over.
this one, and remember, there's 2 of them. Is it this one? So 41.9232, can't see it that well, and 13.8439. Right? So those are the two different ones we're going to use. So I'm sure I can't remember what I just said.
41.9232 is all we want.
So
Is that just a
41.9232,
bigger number, is that correct?
is that what you said?
Yeah.
No, is that because, even though we found it on the right, because it's the bigger number, it has to be on the left?
Yeah, I mean, if you derive, you know, if you use probability and stuff and you derive this equation, this is what it comes out to be. This one's on the left, that one's on the right. But just from an intuitive sense, it makes sense. If you want a smaller number, you have to divide by something that's big. If you want a bigger number, you divide by something that's small. So that intuitively, that should make sense too. But that's not the reason they're there. The reason they're there is if you were to derive the formula, that's what you get. And then the other one is what?
13.8439.
13.8439. Okay. Does everybody see where those came from? Okay. So then we just grab our calculator or something. So the leftmost one, I get 3.0713. And then the rightmost one, I get 5.3447. Was everybody able to get those in their calculator that had a calculator with them? Okay, so again, this is our 95% confidence interval. Not from you. We don't think the average is between there and there. We think the standard deviation of the population is between there and there. So remember, the standard deviation expresses how much variability there is. If the standard deviation is small, that means we tend to get the same value, or close to the same value for most of the observations. And if the standard deviation is big, that means we're tending to get observations that are all over the board. Okay? So that's our 95% confidence interval for sigma. Number 3, is it reasonable to think that sigma is 3? So if somebody says, you know what, I think sigma is 3. Well, remember, we do the same, we kind of play the same game here, right? So think about the number line. You don't necessarily have to draw this out, but I think sometimes it's useful. Here's 3, that's our, what would I call that?
Sigma claim?
It'd be sigma claim, yeah, that's exactly right. So sigma claim.
And would you still have MVD, or is it different?
No, you could do an MVD. Right, so.
Would it be called an MVD or would it be called an SVD?
Yeah. Well, no, it's still because it's just a minimum. MVD stands for minimum verifiable difference, because we're saying, do we think that sigma is different than 3? Well, yeah, we think it's somewhere between here and here, so yeah, we think it's different. What's the minimum amount we think it's different by?
0.0713.
0.0713, but it could be more, right? That's why it's called a minimum verifiable difference. So in this case, the MVD is just 3.0713 minus 3, so 0.0713. Right, so in terms of a picture, this distance right here is the MVD. So putting it all together, we'd say, yes, we have evidence that sigma is different than 3. How different do we think it is? Well, we think it's different by at least 0.0713 units. Could be more. I mean, because, you know, if sigma was actually up here, it would actually, the difference would be more than that. But we think it's at least 0.0713.
How come we didn't do the assumptions?
For this one, you just have to have a normal population. And I didn't tell you that, but I think I meant to in the problem. So I should have actually mentioned that. This is one of those procedures, like the one we talked about yesterday, the T procedure. The T procedure, if your assumptions, if the normality assumption is slightly violated a little bit, or maybe it's not perfect, the T interval does pretty well. People have shown that the T confidence interval does pretty well, even if the assumptions are slightly violated. This one, however, is not that case. This one, if you don't have perfect normality, you probably shouldn't be using it. So I probably should be, I should have said that actually in the problem, but I didn't. The one that actually has a data set with it, we'll talk about that. Let's do the next one. But that's a good point. For all these different things, you should check assumptions, and I kind of left that off there, and I should have put it on. All right, so this one, we're saying there's a company that produces carabiners for rock climbing. And this is one where, if you're going to rock climb on carabiners, you're going to hope the company does some quality control testing, right? You wouldn't want them to say, hey, on average, our carabiners hold the right amount of weight, but the one you get's the one that holds nothing. And yeah, standard deviation would be pretty important if you're making rock climbing equipment. Any sort of safety equipment or anything like that. So they want the standard deviation to be 0.75 kN. KN stands for kilonewtons. So they say, okay, you know what? If we have 0.75 as our standard deviation, we're okay with that. But if it's more than that, we might have a problem. So what we do, or they do, is somebody takes a sample of 16 carabiners and they find out the standard deviation is 1.03. So what is the 16? What is the 1.03? And maybe if we want to think about it, what's the 0.75?
MNS and 75 would be your
Let's take it slow here. What's the 1.03?
S.
That's S. We took a sample, got the standard deviation, so that's S. What is the 16? Sample size, that's N. What about the 0.75?
That's what you want it to be.
It's what we want it to be, but it's sigma claim, right? That's what they're claiming it to be or wanting it to be. So the 0.75 is what we're going to compare this interval
Would
to
that
later.
be the standard they want everything to go by, that sigma claim? That's the standard?
Well, that's what they want it to be, yeah. So number one, what's the point estimate for sigma? So sigma is the true amount of standard deviation out there in this process. What's the point estimate for that? We know it may not be perfect, it may be a little biased or something like that, but we'll just say 1.03. Okay. Number two, let's go ahead and get a 99% confidence interval for sigma.
So we do 16 minus 1, is it?
That would be the degrees of freedom, yeah. So n is 16, so we'll have 15 times s squared times 1.03 squared. All right, so we're going to have to find the two different chi-squared critical values, right? So we have 15 degrees of freedom. What confidence level are we doing here? 99?
Yeah.
So it's going to be the two outermost, right? So 32.8013, is that one you guys got?
Yeah.
So the bigger one's going to go on the left, the 32.8013, and 4.6009, is that the other one? Remember, those just came straight off our chi-squared table. Make sure you square root the whole thing. That's a common mistake that people make, is they don't square root the entire fraction. All right, so I get the left one, 0.6965. rightmost one is 1.8598. Anybody else manage to get something like that? So we're 99% confident that this interval contains sigma. Again, in terms of checking assumptions, we'd have to have a simple random sample, which hopefully I would tell you. I don't remember if I did in a specific example. Hopefully this company would be smart enough to take a simple random sample. Instead of taking all 16 carabiners from the same box or something like that, you'd want to get a mix all over probably. And we'd have to have a normal population. So in reality, what would somebody do you think? If they were going to use this procedure, probably they'd take those 16 values and make what kind of plot? QQ plot. So for the first and second example here, I didn't actually give you the data. The third example, I do give you the data. At least I think that's the next one. Yeah. So the third example, I actually give you the data. So I'm going to have you guys do that one. And on the next example, I am going to have you guys explore the normality assumption. Now let's go ahead and answer question 3 before we get to that. So whenever you're checking to see, what's reasonable, what's not, draw the picture, draw the number line. So our interval goes from 0.6965 up to 1.8598. Here's 0.75 maybe, right? So is 0.75 a reasonable value for sigma?
Yep.
According to our interval, yeah, it is, right? So it's within those bounds there. So an MVD, you only find an MVD if you think there's a difference. We don't think there's a difference according to what we got. So we don't need to have an MVD here, right? Any questions on that? All right, so what I want to have you guys work on here is go to that next example. You're going to have to use Stata or R or your TI or something like that to get summary stats. And then at the end, you're also going to have to do a QQ plot to try and assess whether you think that population from which the sample came is low. Okay? So work on that, and then we'll go over the answer.